Welcome to Part 6 of our Kornucopia ML Quick Start training. This is the 6th of 8 videos for this course. Please visit our website at boditech.com for additional details on downloading the accompanying PDF course notes and other training files. Alright, so we are on the second day of the class on Kornucopia Quick Start. Yesterday we spent our time learning about the primary portions of the syntax for the software. Today we will spend the entire time doing workshops live. I've given you 4 workshops. We'll go through at least 2 of them over the next few hours. And depending how time goes, we will potentially touch on aspects of the last 2, the ball lens impact and the moon penetrator examples. You were given data files for these. They're in the example scripts folder under the appropriate folder for the particular example. And there's also a Kornucopia folder within each one of those that has the M script, which is the solution, as well as a FIG file, which is the result, and a PDF, which is a PDF of the tabbed plots in the FIG file. These examples are intended to walk you through typical Kornucopia workflows, where we're importing 1 or more data files and then doing a variety of analyses that are generally geared at cleaning up messy, noisy data. And the way I'm going to do this is I'm not going to run the M files. I'm going to create them from scratch live in the course, showing you how that workflow would be created and the general concepts of doing a workflow like this. The few slides that follow this are just brief overviews for each one. So I will go over the overview of what the problem is, and then I will starting with the typical shock acceleration processing example. Beyond these 4 workshops, the Kornucopia examples and tutorials that I highlighted yesterday, where there's about 9 or so tutorials and just short of 40 examples, cover a broad range of problems that are all, for the most part, realistic solutions and examples. So I encourage you to explore those as well as you're looking at the software and ideas for your particular application. So the first workshop we're going to do is an example where we're going to take accelerometer data, and it's coming from a physical test for drop of a consumer electronic device. And we're going to take the 3 channels of acceleration data that's in this file. We'll read it in, initially assess it, then we'll do these various steps. We're going to make an adjustment to remove the nominal DC bias. It's always in a physical measurement. Then we'll do a Fourier spectrum calculation to compute the frequency content in the data. We'll use that to judge where the resonance of the accelerometer is. And based on that, we'll set a low-pass filter that's 1/10 of that, and use that to remove distortions from the sensor's resonance in the data. And then we'll reassess the data after that. And then we will integrate the accelerometer data to get velocity versus time. And we'll perform a sanity check relative to theoretical bounds of what a velocity change could be in a drop problem. And then we'll end computing a shock response spectra. So this will give you a good idea of putting together several Kornucopia functions in a typical workflow. And your job, which is our job together at the moment, will be to create a solution to do this. All right, so we will get started. So I'm going to open up a new traditional script. One comment I will make. So MATLAB has 2 types of scripts. The live script allows you to put in some other additional meta-like information and some pictures and things in the script itself. And Kornucopia can be used with live scripts. The reason that I am tending towards the traditional script is the tabbed workflow approach works much better in the traditional script than it does in the live script. And since I suspect many of you are going to be doing problems like I'm describing in these workshops, I would suggest the native traditional scripting is the preferred approach at this time. All right, so I'm going to set my folder as though I was in a working folder here. So this is some working folder that I would have, and the data for this particular problem is right here in that folder, and there's the data file. So the data file that I'm going to open, since this is a text file, I can just pick open, and it will preview what the file looks like in the MATLAB editor. I could also have opened this file up in something like Notepad++ or other editors to look at it. If you're going to read the file in with Kornucopia's read text, what you do not want to do is open that file up in something like Accel, because Accel will interpret the file and then you won't fully understand its format. So if you're going to read it with KRead text, which we are going to, you should open the file up first to see what it looks like in a text editor like the MATLAB editor or a program like Notepad++. So we're going to start creating our script. Normally in a script, the first thing I would put in a script would be some kind of comments. So I have some idea, or anybody who inherits the script in the future has some idea of what we're looking at. So I'm just going to make a simple comment. You could make, a multi-line comment or whatever. This is a workshop. In Kornucopia, we would typically put in a few things right at the top. So the first one we put in would be the K cleanup. So I'm using the tab completion from MATLAB to help me pick the function so I don't have to remember and type everything. So I just type K_CL and then hit tab and I get this. So I'm selecting this. I will generally put 2 parentheses like that and a semicolon. The 2 parentheses are helping me understand that I'm calling a function. I don't have to do this. This function does have some optional arguments. Generally, we don't use them, so I'm not worried about that. But what I'm just pointing out is if I had only done this, that could have been reference to a variable, or it could have been reference to some other thing. So by doing this, it's 100% clear I'm calling a function. So that's going to clean up our workspace, which at the beginning here is already cleaned up. But as we rerun scripts and whatnot, having a cleanup thing is helpful. The next thing I'm going to put in here is the units preference, because when I do my calculations, I want to have some preference of what I have stuff reported in. So I'm typing K units and hit a tab till I get to the preference here. And there's several unit preference choices. We discussed them yesterday. So I'm going to pick the one that's for activate. And if I don't know like what kind of choices there are to choose from, I'm going to put in the question mark initially. And if I just highlight that and hit F9 or right click and select evaluate selection, which is the same as F9, this one line will compute and a pop-up is going to occur. Now, the first time we run Kornucopia, Kornucopia has to load a fundamental program into MATLAB memory. So it'll take a moment the very first time some Kornucopia function is called. So right now that's what's occurring. That's loading up into memory. And Kornucopia will by default start out with a preference, which is the SI system. But most of us don't work in meters. Some might, but many people will have units of millimeter for length and time, maybe in seconds or other things like that. This particular problem we're working with is a shock-oriented problem. So I don't want accelerometer data to be constantly manipulated in terms of meters per second squared or anything like that. I would like it to be in terms of G. So I'm going to be using one of these shock vibration-based unit preferences. And the one that I'm going to particularly pick is one that's got G's, but length's in millimeters and time is in milliseconds, because the shock event is short. And I really don't like looking at plots with time in seconds and e to the -3 or such in the plot. So I'm going to pick this particular unit preference. I'm going to say, okay, so that is now set. It echoes it to the window. And now I'm going to copy this and place it here in replacement of the question mark, so that when I then later open up this script at some other date, it already has the preference set. I don't have to think about it. Now, before I go very far, I'm going to save my preference, or not my preference, my script, and I'm going to save it somewhat consistent with the way it was here, as though I'm going to give that name something a little bit different. I'm getting into the editor section here, and I'm just going to hit save, and I'm going to save my script just as, I don't know, we'll call it example.m. So you will have the actual solution to this problem right here. But what we're doing is we're creating one from scratch, so you get the idea of how you would do this.
Hey, Ted,
Yes.
can you go back to show how you got the units to appear in the parentheses? I missed that part.
This
I
here?
put in you run the K units preference activate and wait for it to pop
No,
up.
with a question mark. So you got to
Yeah.
put a question mark in here. If you do that and run that, that'll pop up the choice. And then you select whatever preference you want. So we had selected this preference.
Mm-hmm.
And when we did that, in the
Okay.
command window, it echoed that that's now the active preference. Then I just copied that string and replaced it here and put it there.
Okay, got it. Thanks.
Yep. Okay, no problem. Okay, so the next thing that I'm going to do is I'm going to create the ADV variable. And that's calling the function k_ADV. And what this does is this creates a nice structured list that'll allow me to quickly access Kornucopia advanced options as I need them. Right now, I'm not using them at the moment, but we're creating it so we can use it in the future. Now, in this problem, I'm intending to, read in raw data, plot it, manipulate it, plot it, do some more manipulations like a Fourier spectrum, plot it. So I'm intending to make lots of plots. And if I put each individual plot in a figure window, I'll have a whole bunch of figure windows open. It'll be hard to manage. It'll be hard to store the data at the end. It's just not a very good workflow when you have lots of plots. So what we're going to do right up here in the beginning is we're going to generate one figure window, and we're going to make it a tabbed-based figure window with a bunch of tabs, much like if you were to go into a lab, bringing a notebook with a bunch of pages, so you can start writing comments on your lab notebook. Similar concept here. So I'm going to create a figure, and I'm going to set the figure equal to some variable. Traditionally in Kornucopia, we would set that variable to fig h, which stands for the figure handle. But this variable on the left could be anything you'd like. And on the right, we're using the MATLAB command figure. Now, the MATLAB command figure has several different name, value, advanced options. So the first thing I'm going to give it is a name. And the reason I want to give it a name is that in the end of this, I'm going to save the figure file. I'm going to save it in a file that's similar to the name that I created. And then in the future, if I have multiple figure windows open and they're named, as opposed to just showing it as figure 1, figure 2, it's really easy to understand, oh, that came from this file or that file. So I'm going to give this a name here. Now, if I just do this, and I run this part of the section, we're going to get the cleanup. We'll say yes to that. The preference is already there, so it's fine. We have an ADV variable, and we have a figure window. And the figure window opens up in the standard figure window size for MATLAB. And if I make a single plot in here, that's not so bad. If I start to make any plots where I make subplots, they'll get pretty small in a figure window like this. Most people nowadays have pretty sizable monitors. And so what a lot of people will do is they'll take the figure window and they'll stretch it open like that. Then every time you generate figure windows, you're constantly stretching it open to something like that. If you then ever want to paste images into PowerPoint, they all end up in various sizes because one time you stretch it this size, next time you stretch it this size, etc. So I'm going to show you a way to add one additional parameter to the figure command so that we can open it up to some size other than the default. So the fully, I could type, the keyword we're going to use is position. So we can type in the whole word position. You can even type it short. Even just POS is sufficient because that'll still be unique with the different name options that are in the MATLAB function figure. And now what this wants by default is a position vector like this. Now, most people don't think in terms of pixels. And so that window was kind of small. And most people might look at that and say, well, when I opened that window before, I wish it was maybe twice as big. So we can do that easily with a Kornucopia function called fig zoom. So if we type k_fig zoom, open parenthesis, we can put in one of two things. We could put in a single zooming factor, which will apply to the X and Y direction of the figure window, or we can put in individually X and Y zooming factors for width and height. I'm just going to put in a single factor. And now when I execute that, the figure window is now going to open up nice and large for me. This will be really nice. The plots will look nice and big. And if I want to have on a particular tab a subplot with 3 or 4 plots on it, it'll be no problem. It'll still look reasonable size. Now, most MATLAB users, if they have a reasonable computer setup, will have 2 screens. And a great approach in MATLAB for 2 screens is you put this figure window in one screen, which I'm going to do off to the right. Unfortunately, Zoom only shows one screen, so you now don't see it. It's off on my other screen. And I have my MATLAB environment in the other window. So what I'll be doing throughout this, I'll be bringing the figure back over to show you what occurs when we put stuff in the figure. Now, normally when I would issue this command, I really don't want this figure to be constantly echoing to the command window. So I would end it with a semicolon. The semicolon tells MATLAB, do not echo the result to the command window. So I'm just going to use home here just to get this stuff out of the way. So this looks clean. So now I've generated this figure window. Now what I would really like is in my figure window, I would really like to have some tabs. So an easy way to do this is to create a set of tabs. MATLAB has native functionalities to do this. If you do that, it's a multi-step process, and MATLAB won't do any managing of the tabs for you. And if you do that with just native MATLAB commands, and you put in lots of tabs with lots of plots, and the plots are made from large data sets, the whole figure window will slow down to a crawl. If we use the Kornucopia's functionality, it adds some additional technology. It helps you manage the tabs with an orphaning technique, and the tabs will behave very efficient. So that's what we're going to do. So I'm going to create a function, not a function, I'm creating a variable. And what I'm going to call is I'm going to call this fig tab set of commands. And the first one I'm going to call is fig tabs create. So what this function allows me to do is to easily create a bunch of tabs in a figure or any other parent. So we'll learn a little bit about parent as we move forward in this example. So for right now, I'm just going to say I want to put 10 tabs, and I want that to go into figure H. So now I'm going to execute that. And now what I have is my figure window, instead of just being empty, now has 10 tabs in it. So you could think of this like 10 pieces of paper in a notebook. And as we go through our workflow, we will pick different pieces of paper and put stuff on it, just like you would in a notebook. Now, when we issue this command, tab stuff is a special type of variable that Kornucopia has. You could kind of think of it kind of like a structure, but it'll self-update as things in the tabs change. And it can tell you pointers to the tab handles, which are the individual tabs, and other things within the figure. So this will be useful to us as we start to create our different plots. Okay, so that's all that we have for the first section. Now what we're going to do is we are going to load in our data. So we have a variety of data that we would like to load in. So I'm making a new section. When I do 2% signs like that, it breaks the script up into sections. And it's realistic workflows. Breaking your script up into sections is a good idea. So you can compute it in bite-sized chunks, look at the result, and go to the next section. So I'm just giving a little title here. I want to load my raw Excel data. And now I want to use the function kReadText. Oops. So here I hit a dash, not an underscore. That was a mistake. So I want to use kReadText. And as we showed yesterday, if we hit F1, the F1 key while highlighting the function, this quick pop-up occurs. And I can click here to get a little template, which will go into my paste buffer. And with that template, it will allow me to paste this little template of stuff to fill in. So at the very top of the template information gives you a description of what's going on here. I'm going to be walking you through this. So for brevity, I'm just going to remove that. I'm going to reference a data directory and a file name. So the data directory is here. So I could literally go and copy this and put that in here like that. And then that would work on my computer, great. If I gave you this script and you didn't happen to put the whole Kornucopia Quick Start training session in this particular folder, then this wouldn't work for you. So I'm going to use a different approach. It's a little more generic. What we're going to do is we're going to put in what's called a relative path. So from where I am, so this is where this script is, I go up one directory and then down into the data folder to where the data is. So the way that that would be coded would be 2 dots \data. So that 2 dots means go up one directory, and then from there, go into this directory data. So that's what we're doing there. And now I'm going to specify our file name, and our file name is Accel.data. I'm just going to copy that. So this is our file name. And if we had typed a quote in here, I mean, a question mark, and we ran this, we would get an interactive pop-up. And you could go browse around and find the file. So that's great if you're doing a one-time thing. The negative of that is if you then later save the script and you later open it up, you don't know where the file is. You got to browse every time. So this approach, while maybe a little manual, I think is more robust because you've hard-coded into the script, where the data is and what the file name is. This next line here is a MATLAB command that's going to combine the data directory and the file name. And so it'll handle whether or not I had an extra slash at the end or not. It handles all that kind of issue. So it's a nice thing to make a full qualified path length for a file. Now, the delimiter is what is delimiting the columns and the tabular part of the data. This particular file, it's a comma. Other files, it might be a semicolon, it could be a tab, and whatnot. In the event it was a tab, you would not click here and hit the tab key. That wouldn't do anything because MATLAB interprets that specially. You would do /T if the delimiter in your files were tabs. In this case, it's not, it's a comma. So I'm putting in the comma as the delimiter. Now we have 3 groupings, this grouping, and then this one, and this one. And what these groupings are geared at, as we discussed yesterday, they're geared at finding identifiers that identify different sections to the example file. So in this particular example file, I don't really have a tremendous amount of stuff in the top of the header that I want to really process. So I'm going to just ignore the initial start string and just put in an empty, so it'll start right from the top of the file. But relative to the column names and stuff, I can see the word time is here, and I don't see the word time anywhere else up here. So I can use the word time for that. So I'm going to make this an empty, which will mean start at the beginning of the file. I'm not going to shift it all, so we'll leave that as an empty as well. We will start searching for the column header row with the word time. Since it's actually on the row of interest, we're not going to shift up or down in the file, so this will be kept at 0. And in this particular file, the different data sets are in different columns, and it's just all data to the end. So there's nothing for me to search for to determine the end of the file, so we leave those empty. So that's what we're going to do, and then we're going to read in our file. So if I just run this section, I'll close this. I run this section, it's quickly read in the file, and now there's a variable raw over here. Now, because it's a Kornucopia data type, we generally would echo it to the command window like this to see a look, or we might use the variable viewer, the Kornucopia variable viewer, bar viewer. And we can put in the variable name, or we could leave it blank and select it out of a list. Here I'm putting it in as an example, and that'll open it up in a browsable variable viewer. This is a variable viewer, not an editor, so you can't edit anything, but you can quickly see what you have. If I was to go over here and look at it in the MATLAB variable editor, if I open that up there, it kind of shows like a structure, and you can see there's data, you can see there's units, You can see there's various properties, but like it's very hard to look at it this way. It's very separated. It's not holistic. So in general, with Kornucopia, you do not use on Kornucopia variables the variable editor. Instead, you generally will echo them to the command window or use the variable viewer. Now, let's go get the main header out of this. So I'm just going to hit home here for a second. So in this variable raw, remember we have these things called props. And in the props, there's user data. I'm doing .tab completion to generate this. And because we didn't say anything about the dataset header, all the header stuff above the table, in other words, all of this stuff up here, that is stored in the main file header. And there it is in the main file header. And we want to get that main file header because maybe we'll add that to the description to our variable to give a more better description than what we currently have. The current description just says the name of the file. Well, what we can do is we can do something like this. So all I'm doing is I'm delving into the properties of the variable raw, getting this cell array, and I'm setting that to some variable named header. And now I'm going to change the props description, which currently, if I highlight that and hit F9, is just the name of the file, which was showing here. I'm going to reset that to be header. So when I do that, I didn't run the header line before it. So if I do that, what I'm doing is I'm highlighting and hitting F9 for that to compute. So now we have this nice variable that clearly has some nice information. It's easy for me to see. And I can use that if I want to maybe present that as part of the figure window results of this particular problem. Now, we're ultimately at some point going to be applying a filter and doing some things. So knowing something about the computing sampling rate of the data is very helpful. So most people would compute a sample rate in traditional MATLAB parlance. You would look and you would say, if I took the time, the second row of time minus the first row of time, and maybe set that equal to some variable like fs. Most people would do something like that, and then this would be the sampling increment. A quick note, during my live presentation here, I should have given this variable a name like delta t, as it would be a time increment or sampling increment, not the sampling rate fs, which would have been the inverse of what I just computed. This is dangerous to do because you don't know definitively that the data came at a constant sampling increment, especially if your data comes from simulation models. It's highly likely it doesn't have a constant time increment. So instead of doing this kind of thing, Kornucopia gives you some nice easy functions to calculate sampling rate and whatnot. So the function we're going to use over here is k underscore, and if I type SAMP, I have sampling frequency, sampling increment, or the sampling Nyquist frequency, which is just half the sampling frequency. So I'm going to tell it to give me the sampling frequency, and it's going to say, give me your time vector. So my time vector is just the vector of the time column out of the data. So when I do this, Kornucopia will check that the entire time increment is a constant relative to a small tolerance. And you do have controls through the advanced arguments of this function to change that tolerance if you so choose. But now when we compute that, it computes nicely the sampling increment. And it returns it in an intelligent frequency-based unit, and it returned it in kilohertz. The reason it returned it in kilohertz is because up here, our unit preference had time in milliseconds. And if you looked at the full detail of that unit preference, you would see that the frequency is in kilohertz. In fact, I can show you that live because we could say k underscore units preference list. and we can have it echo the list of all the unit preferences. And the one we're using is this one here. And you see that the frequency right here is in kilohertz for this particular unit preference that we're using. All right, so now we've got a sample rate. Now that sample rate shows us kind of a funny thing. It's 5,000 kilohertz. So if we want to maybe present that in some plot later or whatnot, maybe we would like to show it in terms of megahertz. So that's easily done. We would just say, hey, Kornucopia, please convert that. So that's using dot convert. And remember, we hit dot after a Kornucopia variable, hit tab, and it'll give us the methods, which are lowercase things, and the properties, which are uppercase things. So convert, data size, toStruct, and toTable are the methods that Kornucopia's variable supports. So I want to say I want to convert that, and I want to convert that to megahertz. Now, Kornucopia is case sensitive with units. Like big M is mega and little m is milli. So it's important that you type this all correct. If you type something like this, Kornucopia will give you an error like I'm going to show here, and it says, hey, I don't know what this is. And, gives you some more explanation. So here we'll fix that and put in the correct unit. And now if I compute that, you'll see it'll echo. Now it's showing it in a more nice 5 megahertz style. It'd be nice for us to go plot the data. I'm going to first plot it, ignoring the fact that I made this tabbed figure, and we'll plot it like quickly traditionally. And then we'll put it into the tab figure, and we'll first plot it all together, and then we'll plot it separately in using subplot. So first, let's make the plot quickly. So I'm just going to make another region here. All right, so if I'm just making a plot all by itself, I would issue a figure command. And I would say k_plot. And now what do I want to plot? So I'm just echoing here against the raw so I can see all the columns that are dependent. This is the first one's the independent, which is time. All these columns have values of acceleration. So I can put them all on one plot. So I could literally just do this, raw. I could issue that, and a plot window will come up with all the data. And the data is labeled X, Y, and Z. That's coming from the column names of the 3 dependent columns of the data. You can see time is labeled milliseconds because the time is in milliseconds. And the acceleration axis here is in Gs. There's no particular label here because Kornucopia didn't see any common words from the 3 column names to pull off to make a label. We'll show you how we're going to override that in a few minutes, and we'll put a manual label on. But this kind of curve is a little bit messy. It's a little bit hard to work with. So what we'd rather have is 1, not have it in a separate figure, but in our tab figure. And 2, it would be better if each one of these with its own plot within the figure. So that's what we'll do instead. So I'm going to now get rid of this, and we'll go back to trying to work with the tab plot. So one of the things I showed yesterday was a basic template outline of tab plots. I'll just quickly pull that up to show you all again what that looks like. So at the very top of the figure, we would have this kind of thing, which is what we already created. And then when you're in a particular section and you want to make a plot, there's 3 basic things. You put these first 3 lines, which state which tab we want to be the current tab that we're going to work with. We empty it out to make sure that there's nothing in it so that we don't end up having plots pile on top of each other. And then we would generally name the tab something intelligent because right now they're just labeled 1, 2, 3, 4, like page numbers of a book. Then you would issue whatever plot commands you want to plot. And when you issue those commands, you're going to use the parent advanced option to point at the tab so the plot knows where to go. Otherwise, if you don't do that, the plot's going to go into just the back side of the figure. It'll be behind all the tabs, and you'll wonder where's your plot. And then the last thing here is kfig tabs display. That'll tell Kornucopia to take the figure window and make the current tab that you just plotted, make that the page that you see, because all the tabs are stacked one on top of each other. So this allows you to then see the tab of interest. So this is the basic template we're going to utilize. First thing we're going to issue is a current tab H variable. So again, you don't have to call it this. You can call it my tab, whatever you want. If you choose to call it this kind of current tab H thing, then if you leverage any of the Kornucopia examples, you'll see that they all follow this kind of terminology. And you can literally just copy chunks of code out of the example into your script and just use it almost straight up without very few modifications. So tab stuff main is the special variable that's pointing. Remember, tab stuff main has the pointers to the thing. And so what we're going to do is dot, so it behaves kind of like a structure. We're going to pick a particular tab, and we're going to pick the tab we want to plot in. So the first tab that we want to plot in here is going to be tab number 1. And we want to make sure that the tab is empty. And initially will be empty, but if you, as you develop the script, you rerun sections a few times changing things, then the tab would not be empty. So we generally want to clear it. Otherwise, you'll just keep piling stuff on top of each other in the tab. And I'm taking advantage of the tab key to self-complete so I don't have to type so much. Now, I have not executed this command yet. I've just typed it in the editor. So if I type current tab H dot and hit tab, MATLAB says, I don't know what to do. There's no completions found. That's because at this point, it doesn't really know what this is because this has not been executed. As soon as I execute that, now when I hit the tab completion next to here, it says, oh, this thing's an actual tab handle. And so then it gives me all kinds of stuff you can pick about on a tab handle. It's a pretty large list. Let's not worry about too much here. We're just going to pick easily the title. And what we're going to put in here for a title is just a simple string. So we'll call this our raw Excel plots. So that's the first part of what we're going to do. I'm going to do now the last part, fig tabs. I'm going to pick display and current tab H. So I could literally just copy that. So that's the last part of our little bracket. So this is going to tell us what tab to print in. We're going to make some plotting commands here, and then it's going to put it into this, and then it's going to show that tab to us up on the screen. If I just plot everything on one thing, I'll get a bigger version of what I showed earlier. That's a bit of a mess. So instead, what I want to do is I want to create subplot to put the plot in. So I'm going to create a subplot here. This is a MATLAB command. And a subplot asks how many rows and columns you want to do for your plot. So we're going to make a 2x2 layout. And we're not going to start in the first quadrant. We're going to start in the second quadrant with our plot. And you'll see why in a moment. And then I'm going to add the parent command. So maybe I can spell the word parent. And I want the parent to be pointing at the current tab. If I don't add this command, if I do not add this command, the subplot will be pointing at the base figure itself. And then this will not go on the tab that you want it to. So this makes the subplot go on the tab we want. Now, if we just execute this, we've produced an axis, and you can see it's roughly 1/4 of the area of this tab. And now we'll be able to put a plot in there. All right, so with our subplot, we now want to plot something into the subplot. So what do we want to plot? So let's go plot the raw data. Now, I'm going to just type in the raw data here. Now, I could type something like this. I could say I want to plot in here time and X, which are these two sets. I could issue a command like that. if I issue a command like that, since the subplot was just created before this, that'll be the hot axes, and by default, this will go into that subplot. So I could do that. And if I run this, we'll have the x-axis plotted like this. It'll automatically label the things, label subplot and everything. I had to make no extra effort to do that. Now, I would like really that plot to have a few things. So one of the things I would like is for it to have a grid. So when we do plotting, we have the choice of feeding in independently X and Y data or giving it the X and Y data all together in one. And this is the form that I'm using. And this will generally be the form that almost all Kornucopia examples will generally leverage. So that's why I'm putting the square bracket here to skip the second argument of the plotting command. And now I want to turn on the grid. So how would I do that? You're not sure probably what to do. So one is we could click on here for help. We could open up the help page. We could scroll down to the advanced options, and there's a lot of them. They're listed alphabetically, and here's grid. We could go down here to learn more about that and click here in the help system and learn about the different choices for grid. So you could do that kind of thing. Or we could take advantage of the fact we had that ADV variable we made. So let's just demonstrate that. So I'm going to do ADV dot tab k underscore plot. I got to get for the function. Dot tab. Here's the list of stuff. If I scroll down here to grid, there's grid. I select that. Dot tab. These are the options. So I would like both the major and minor grid to be turned on. So now if I rerun that, my plot now has the grid on it. I now want to go and put the other three plots on. So I'm just going to literally copy this because I'm not a glutton for punishment. I don't really like to type if I don't have to. And I'm going to fill out spot 3 in the grid and spot 4 in the grid. And this is going to be the y-axis. And this is going to be the z-axis. And now we have the three plots. Now, the way it's plotted right now, this looks to be, quite large like the others, but it's a little misleading because the scale is different than the other graphs. And actually, each set of graphs has different scales. So I'm going to show you a nice little feature in Kornucopia that will allow you to have Kornucopia figure out and automatically scale all the graphs that have the same scaling. So what we're going to do is before we issue the plot, I'm going to make some temporary variable, and I'm going to set that equal to a cell array. And I know I'm making 3 plots, so I'll have the cell array of 3 elements. So this is a MATLAB command that just generically makes an empty cell array. And it's just an empty cell array with 3 buckets to put something in. It defaults to empties, and empties default to the numeric double format, but we can ultimately put anything in these buckets. So what we're going to do here is when we generate this plot, we don't want it to echo. We're going to set the output of this plot to this variable. And we're going to just put this in a couple more times for 2 and 3. And all we are doing is we're getting a set of handles for the 3 plots. So now if we just rerun that, the plots will look the same as before. I will just demonstrate they're still the same. But now this temp variable has some structures in it that have stuff about these plots. What we can do is we can take these outputs and we can tell Kornucopia with a function kplot match limits. It says, hey, give me a bunch of plot handles or whatnot. So these are actually, these structures are really a structure of handles of this plots. So I can feed this in there. And I can say, take the X and Y axes and look at all the data and make them all come up to the same axis. So now, right now, they're not the same. This is 600 and 800, 1,000 minus 400, 1,000 minus 800. Once I do this and pull that back up, now they're all the same. So now you get a more fair feeling of what does this signal look like compared to the other two. Now, sometimes people want to put things on plots. Like one of the things somebody might want to have is, what is the max value of the acceleration? If you took any of my previous DSP classes, especially on physical measurements or transient FEA, I told you the peak acceleration in the time domain is usually pretty useless. Nonetheless, people like to see it sometimes. So let's go put on these graphs to echo what the peak value is of the acceleration. What we're going to do is after each subplot, we're going to issue a command and we're going to use the display on figure command. We're first going to make a text string of what it is we want to show, and then we will display it on the figure. So the text string is going to be created by concatenating an actual string. So we're going to make the string peak absolute, abs is short for absolute, Accel equals, comma, and now what we want is we want to take the thing we're plotting and compute the max of it. Now, the way we have done this right now, we've referenced a different column in the plot every time. So I'm going to change up one more thing here. What I'm trying to do is I'm trying to walk you from what you might traditionally do to think of slightly different and be a little more efficient with your workflows. It really helps when you're dealing with lots of stuff. So I'm going to make a variable toPlot equals raw. There's nothing magical about this name. It makes sense. And then what I'm going to put in here is I just want toPlot to be plotted. Okay. And I'm going to do one additional thing. I'm going to set the dependent column to be X. So now I'm going to quickly modify the 3 plot commands to be of this nature. And I'll change that X to a Y and this to a Z. In the second workshop, we'll clearly see the advantage of using the dependent column here, especially when we have stacked data sets. I actually showed an example of that yesterday. Coming back here to our text, I can then compute the absolute value of toPlot looking at the X column. That would compute the absolute value. If I put max here, that'll compute the max of the absolute value. And then if I do one more thing, which is I want to turn that number into a string, that will turn it into a string. And if I want to control its format, I can control its format so I don't have lots and lots of digits. If I execute that and execute that, I now made this nice string statement, which I can now easily add onto the plot. With the display on figure command. So it asks for location on the plot. So when I go look at my plot here, it's asking for some location on this plot. We have the choices of looking at this from a parametric 0 to 1, 0 to 1 kind of coordinate perspective, or we can, with an ADV setting, choose a combination of the actual values in units, like 4 milliseconds, or 400 Gs or things like that to locate on the plot. So we're just going to choose the normalized coordinate approach, which is the default. And I'm going to tell it to turn a box on so that it's boxed with a white background so it stands out on the plot a little better. So let's just rerun this section. And now we've labeled that for our first one. So I'm going to copy that to get labeling on the next two. Oops. So this is just going to be Y. And if I wanted to be a little more sophisticated, I could have also done this with a for loop and made it have even less code. But I'm trying to somehow balance showing you some different features and not making it too complicated. So now we have generated this nice set of plots that's all auto-scaled, and we have a nice little labeling of some piece of information. This particular data set, there happen to be three things. There's an open spot here. So I could choose to add some additional text in there. I will just make a brief kind of version of that. So when I go to do this, on these commands, I didn't issue any parent command. So they by default went into whatever was the hot axis, which was the plot right before it. Here, I'm going to have to specify a parent command. And what I want to specify is the current tab handle itself, which is the canvas that these plots are going on. And I want to put it in the upper quadrant here. So that would be a quarter of the way over and 3/4 of the way from the bottom, because the MATLAB counts from this bottom left corner for coordinate directions. So one final shot. And we have a little thing here. Now in the real example that you're going to get, I put a bit more commentary about what the data is. That concludes part 6 from our Kornucopia ML Quick Start training. The rest of this first workshop example is presented in the next video, part 7. You can access that video via the link provided on our website.